Okay, so just going to record a video about more about tournaments. So the stuff I'm going to talk about today is out of section 7.4 and 7.6. And it's sort of focusing on Hamilton stuff for tournaments. So here's our first theorem. Every tournament has a Hamilton path. So if you recall, a tournament is just a directed graph where between any two vertices you have an edge going one direction or the other, but not both. So that's a tournament. And a Hamilton path is just a path that uses every vertex. And keep in mind that we're talking about directed graphs, so this has to be a directed path. So all the edges go in the same direction along this path. So that's the theorem. And so let's prove it. Let's say we're talking about a tournament of order n, and n is at least 1. You know, graphs and digraphs, we only consider ones that have at least one vertex. So the order is at least 1, and we're going to do a proof by induction on n. So the base case is going to be when n equals 1, there's just one vertex. The tournament with just one vertex is a pretty simple thing to look at. Here it is. And sure enough, it has a Hamilton path. This would be a really easy path that starts and ends at the same vertex. There's no edges to use, so you could call it the trivial path. It's the path that starts and ends at the exact same vertex. So that was easy enough. So let's talk about the induction step. I'm going to draw a picture. So here's T. For the induction step, typically for proofs by induction, you know, we remove something and then we talk about the smaller object, and because we're doing a proof by induction, we know some facts about the smaller object, and then that helps us put the removed thing back in. So that's a very vague description of proofs by induction, but I'm going to have a special vertex that I call V. Inside here, there's going to be the rest, so I'll call that T minus V. And of course, I just mean like removing a vertex in the same sense that we always talk about removing a vertex from a graph. So inside this bubble, I'm going to draw the digraph T minus V, which just means it has all the vertices except for V, and it has all the edges as long as they don't touch V. So let me actually write something as I go. What do we know about T minus V? Well, we're doing a proof by induction, and we're showing that every tournament has a Hamilton path. So we know that T minus V, since it's a smaller tournament, it has fewer vertices, it should have a Hamilton path. And let's say we can give some names to the vertices in this Hamilton path. Typically we would denote a path by just the sequence of vertices in the path. So why don't I say it's like V1 through V sub n minus 1. There would be a total of n minus 1 vertices in here, of course. And so why don't I draw this in the picture? I don't know, maybe V1 can be here, V sub n minus 1 can be here, and I'll just go around this way. This is a directed graph, and this is a directed path, so I'll draw the arrows indicating the directions. And what are we trying to do? We're trying to show that T has a Hamilton path. So I would like to show that T has a path that uses all the vertices, and this kind of goes a long way already, because already I have a path that uses all but one of the vertices. And this is why I was talking about like the big picture for a proof by induction is you use what you know about the smaller object, and we know this smaller tournament it has a Hamilton path, and then we have to put back in this thing that we removed to make the smaller object. I have to find a way to somehow loop this vertex in with this path. Of course, I could do that if, and what makes this slightly, I don't want to say difficult or complicated, but maybe more difficult or complicated than it could be, is we have to pay attention to the direction. What I can hope for is if there's some point in this path where I have an edge going towards V and then an edge from V going to the next one, like maybe I will, well, for the purpose of the picture, I'll just draw on top of this. What I'm really looking for is if I could find something like this, then my path would go like that, and that would be a path using every vertex in the whole tournament. So I just have to show that I can find something like this. And what do I mean specifically? If I can find some I such that, say, VI has an edge going to V, and V has an edge going to the next one, VI plus 1, then we're done. Also, actually, maybe I should have said this first. There could be a couple of other easy ways that we could be done. For example, if V has an edge going directly to V1, then I would just put V at front. I would go V and then V1, and then I would go all the way around. So we would also be done if V had an edge to V1. We would also be done if we could put V at the end, meaning, and we could put V at the end if the last one, V sub n minus 1, had an edge going to V. Oops, yeah, when I should be saying, like, these are edges of the tournament. Okay. So now what I'm going to say is we definitely have one of these things that we said. So here's the argument. And remember, this is a tournament, so every possible edge goes one way or the other. So how could we fail to find a Hamilton path? Let's go through the steps. First of all, V could not have an edge going to V1, because if it did, then we would immediately find our Hamilton path. So suppose that doesn't happen, because if it did happen, we would immediately be done. Yeah, sorry, so this says V comma V sub 1. So what does that mean? That means that you have the edge from V sub 1 to V, because it either goes one way or the other. So I have actually, let me even draw another picture here. And I'm going to draw these in a line so it's easier to look at. So here we are so far. If I had an edge from v sub 1 to v, then I would immediately be done. So I must not have that, meaning the edge goes the other way. It goes this way. And then if I had the edge from v to v sub 2, then I would be done. Like if this edge was going this way, then my path would go like this, this, and then this. So it can't go that way. It would have to go this way. So what am I trying to say here more formally in the proof? Now if v to v2 was an edge, then we have our Hamilton path. Otherwise, it must look like what I drew. The edge must go from v2 to v. And now basically I'm just going to keep repeating. If the edge went from v to v3, like if the arrow was pointing down to here, then here's my Hamilton path. I would go here, 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 and then through the rest. So continuing this logic, we're going to find a Hamilton path unless this edge goes this way, the next one would also have to go this way, the next one would have to also go this way. So all of these edges would have to point up towards V. So all of these edges like V1, V, V2, V, all the way up to V sub n minus 1, V. But then what did we say? Well, now that we know the picture looks like this, I can show you the Hamilton path. You just go from here all the way to the end and then to V. In other words, you can go from V1 all the way to Vn minus 1 in this order and then up to V. So no matter how it looks, we can find a Hamilton path. Okay. What else about this stuff? So I just want to note that some tournaments only have one Hamilton path. I can draw a tournament pretty easily. I'll just draw a tournament on 5 vertices, but you're going to get and actually it's going to look like kind of a mess. Maybe I should explain what I'm doing. This is going to be a tournament, and the edges are just always going to point from the smaller number to the bigger number. So I already went 1, 2, 3, 4, 5, but of course I have to draw the edge from 1 to 3, and that's going to point this way because it just points to the bigger number. In fact, the way I've drawn it, it goes from left to right. So another way of saying this is that all the edges they point from left to right. And as I said, this is going to end up being a mess when I'm done, but okay, I think that's the last one. In any case, this would, and of course you can do this, I did this for 5 vertices. You could do this for any number of vertices. Just go from 1 to n and draw all the possible edges, and all the directions just go from left to right. Such a tournament can only possibly have one Hamilton path. Of course, there's a really easy Hamilton path to see where you just go 1, 2, 3, 4, 5. And that would be the only Hamilton path, because there's no way to go back to a smaller number. The edges only go from smaller numbers to bigger numbers. So if so first of all, I'd better start at 1, because if I don't start at 1, there's no way I'll ever get back to 1. And so I have to start at 1, and the very next vertex had better be 2, because if I go from 1 to something else, then I'm never going to be able to get back to 2. And then similarly, the one after that has to be 3, because if it's something else, then I'll never be able to get back to 3. So I just have to hit the smallest number, then the second smallest, then the third smallest, and I just have to go in order. That's the only way to have a Hamilton path in such a digraph. By the way, a tournament that looks like this, meaning a tournament whose vertices can be arranged, say, from left to right, where all the directions go from left, all the edges go from left to right, we call such a tournament a transitive tournament. Okay, so yeah, I just point that out because we just stated a theorem saying every tournament has a Hamilton path, and for some tournaments they really only have one. All right, so let's talk about another sort of similar theorem, this time about Hamilton cycles. So a tournament with at least 2 vertices has a Hamilton cycle if and only if it is strong. And remember, strong is also known as strongly connected, and that just means that between any 2 vertices there's paths going both ways. So there's a path from U to V, and there's also a path from V to U. And of course we're talking about directed graphs, so just because you have a path from U to V doesn't automatically mean that you have a path from V to U. But for strongly connected tournaments, they do. Between any pair of vertices, there's a UV path and a VU path. Right. So I'm really just going to give like a proof sketch of this. Because the ideas are similar to what we've been talking about. And one of these directions, because this is a bidirectional thing, it's like an if and only if statement, one of these directions is easy. The forward direction is easy. I'll show you. Suppose we have a tournament and it has a Hamilton cycle. So I have all the vertices, and there's a directed cycle, so all the edges point, you can say either clockwise or counterclockwise, but it's the same direction. So you can follow the directions, go all the way around. If you have this, and keep in mind, of course, you have other edges, but I'm not going to talk about the other edges, so I won't draw them. But if I have this, then of course this is strongly connected, because look, give me any 2 vertices, like, I don't know, this one and this one. I can have a path from this one to this one by going around this way, and I can have a path from this one to this one by going around the other way. And that's going to be true for any two vertices. Give me any two vertices in this picture, and I can get from the first one to the second one by going one way, and then from the second one to the first one by going the other way. So that's the forward direction. If a digraph has a Hamilton cycle, and in fact, if any digraph has a Hamilton cycle, it doesn't need to be a tournament or anything. It just needs to have a Hamilton cycle. Then it's automatically strongly connected. So let's talk about the other direction. So we're going to assume that it's strongly connected, and then we're going to show that it has a Hamilton cycle. And this is just a proof sketch, so I'm not fully justifying everything I'm saying. First of all, I'm going to claim that T must have a cycle. Basically, that's just because we're assuming it's strongly connected, so if you give me any two vertices, you know, there's a path going this way and also a path going the other way. And if you have two such paths, even if they cross each other somehow, there has to be a cycle somewhere in there. So this digraph has to have a cycle somewhere. We're not saying yet that it has to have a Hamilton cycle. I'm just saying that it has to have some cycle, because otherwise, how can you have two vertices with paths going both ways without making a cycle? Now that we're convinced that it has a cycle, consider the longest cycle, or whoops, I'm doing the thing I always do. Consider A longest cycle, because of course there may be a tie, and so just pick one. If there's a tie, just pick one of the longest cycles. And of course, well, what we're trying to show is that the graph is Hamiltonian. So we haven't shown this yet, but what we want to show is that this longest cycle is the Hamilton cycle. So what we're going to do is we're going to proceed by contradiction and assume that this is not a Hamilton cycle. That just means it doesn't use every vertex. So say some vertex V is not on the cycle. So here's a picture. I've got V. I've got a cycle. And let me just describe out loud how the proof sketch gets finished. The proof sketch gets finished by arguing that I can find a way to loop V into this cycle. Specifically, what I'm going to do is and this is very, very reminiscent to this picture. This picture, we were talking about paths, so it didn't have to go all the way around, but what we had was a long path, and I was trying to loop in another vertex. So I looked for two consecutive vertices on the path, just so I could sort of like follow the path up to this point, and then go to V, and then go to the next one that was supposed to be on the path, and then follow the rest of the path. So I'm sort of looking for two consecutive vertices such that I can go this way and then this way. So I would like to find two consecutive vertices on this cycle so that I can go this way and then this way. That's what I would like to find. And let me just, I'll just say out loud why I'm confident I can find that. First of all, actually, let me sort of cross these directions off, because we know it goes one way or the other. Consider all the edges from V to all of these vertices. If they all go this way, if they all go away from V, then this is not strongly connected, right? Because we're saying that this is strongly connected, meaning from V to any vertex on here, there's a path going from V to there, and there's also a path from there going back. So the edges can't all point away from V. There has to be some edge pointing towards V. And also they can't all point towards V, because then, again, it's supposed to be strongly connected. So I'm supposed to be able to get from V to these vertices. And if all these edges pointed towards V, then I couldn't get from V to anywhere. So they're out of these edges that go between V and these vertices. Some of them have to go out of V, and others have to go into V. And then if you think about it, once you have some of these vertices have edges like from V to them, and then other vertices have edges from them to V. From that point, it's easy enough to see that you have to have two that are next to each other. You have to have two vertices on the cycle that are consecutive, such that one goes out to V and the other one comes in from V. In other words, sorry, I crossed this off, but I'm going to draw it back. You have to be able to find two that are like this. So that's the proof sketch. And it's like I said, I didn't go through all the details formally, because the idea is similar to last time. You have a long thing, and you want to make it longer by looping in an extra vertex, so you look for two consecutive vertices in your long thing, whether it's a Hamilton path or a Hamilton cycle, and try to figure out a way to loop in that last vertex. Okay. Whoops. What did I want to do here? Okay. So here's a theorem. Every vertex in a non-trivial tournament belongs to a triangle. Whoops. And actually, I'm pretty sure I wrote that down wrong. Strong. There we go. Every vertex in a non-trivial strong tournament belongs to a triangle. And I'll describe this as a proof sketch because, again, it's kind of a similar situation. We're building off of what we proved before, and we're also using similar ideas again that we already used. So suppose we have a non-trivial strong tournament. We just showed that a non-trivial strong tournament has a Hamilton cycle. Right? Yeah, if T is a non-trivial just means at least two vertices, and it's strong implies that it has a Hamilton cycle. So we know that it has a Hamilton cycle. Now, pick any vertex, because again, I'm trying to show that every vertex belongs to a triangle. So I'm going to pick my favorite vertex, and of course it's on the Hamilton cycle because every vertex is. Woo, excuse me. Now, watch what I do on the picture. Keep in mind a triangle, of course, means a directed triangle, so I'm referring to like 3 vertices where, you know, it's like a directed cycle with 3 vertices. So watch what I do on the picture. We know we have this Hamilton cycle. Let me look at the second vertex after V. Which direction could this edge go? Well, if it goes this way, then I see a triangle right away. Otherwise, it goes this way. And then look at the next vertex. Draw the edge to V. That has to go one way or the other. If it goes this way, then I see a triangle. Here, here, here. So if it went that way, we would be done. So assume not. It goes this way. And then I'm just going to keep going. Which direction could this edge be? If it's this way, if it's towards V, then I see this triangle. So what if it's that way? So what I'm going to get is I'm going to conclude, what I'm doing is I'm going around the cycle and I'm saying, if I don't have a triangle, which direction do these edges have to go? And I keep concluding that these edges have to go away from V. But look, now I got to the end, and here's my triangle. Right? So either what this proof sketch basically shows, if you followed what I drew on the picture, is either I'm going to find a triangle by examining the directions of these edges, or when I get to the end, I'm going to find my triangle. So any way I do it, I'm going to find a triangle that contains the vertex V. And then, so this is the last thing I wanted to show you. In a non-trivial tournament of order n, every vertex is contained in a cycle of every length from 3 all the way up to n. So you give me, so give me a non-trivial tournament, and give me any vertex and tell me any length of a cycle. And you can pick a length, any valid length. So the shortest possible cycle would be 3, the longest would be n. Give me any length of a cycle, and I can find a cycle of that length going through that vertex, whatever length you gave me and whatever vertex you gave me. So, right, and again, this is just sort of putting together previous ideas. Yeah, so maybe I'll just kind of go quickly here. You give me a vertex and you give me a length. First, I'm going to find a triangle containing V, and we already know we can do that because of theorem 7.27. And, well, if L was 3, then I'm very happy, because I'm done. If L is larger than 3, then what I'm going to do is I'm going to take this triangle containing V and try to make it longer. And what can I do to make it longer? And basically I would like to make this longer one by one. So first I would turn it into a 4 cycle, and then a 5 cycle, and then up until whatever length you give me. And I can do that by looping in one vertex at a time. So, in other words, I'm going to find another vertex such that I can go like this, and then, well, if L was 4, then I'm done, but if I need to make it longer, then I can do it by looping in another vertex. So here's my cycle of length 4, and then I'm going to make a cycle of length 5 by finding 2 consecutive vertices, maybe this one and this one, so that I can go from here to here, and then here to here. And then my 5 cycle is going around like this. And I basically keep doing that until I achieve the desired length. So this property is called being pancyclic. Pancyclic means that you have a cycle of every conceivable length, all the way from the shortest conceivable cycle of length 3 all the way to the longest, which just has all the vertices in the whole graph, so it would be length n. And of course, that pancyclicity is stronger than Hamiltonicity, because if a graph is pancyclic, then of course it's Hamilton, because it has a cycle of length n. So yeah, pancyclicity is another property sort of similar but stronger to Hamiltonicity that is commonly studied in graph theory. So, oh, and I am almost out of time for the video, so I'm going to stop here.